You know, when we think about the absolute most hostile environments a human could possibly try to survive in, I feel like our minds usually go straight up, right?
Oh, definitely. Like the vacuum of space, the extreme cold.
Yeah, just that incredibly fragile metal tube keeping a handful of astronauts alive. But there's an environment right here on Earth that is, honestly, arguably just as unforgiving.
Deep ocean.
Exactly, the
Yeah.
deep ocean. I mean, the pressures down there are crushing, the darkness is absolute, and the machines we've built to conquer it are, well, they're every bit as complex as a space shuttle.
Yeah, they really are absolute marvels of engineering.
So today we are going on a deep dive into some really comprehensive Wikipedia articles detailing the history, the technology, and the massive geopolitical impact of the nuclear submarine.
Right. And our mission today is basically to figure out how strapping a nuclear reactor to a boat fundamentally changed naval warfare.
Which is wild to even think about.
It is. I mean, it turned these incredibly fragile, temporary underwater vessels into apex predators with just virtually unlimited range.
Yeah. But of course, we also need to examine the terrifying hidden costs of harnessing atomic power in the deep sea, because there are always costs.
Oh, absolutely. And to understand the sheer scale of the disruption that nuclear submarines caused, you really have to look at what militaries were dealing with before they existed.
Right, the conventional diesel-electric submarine.
Exactly, because if you were a submarine captain in, say, World War II, you weren't really commanding a true submarine.
Right, you were basically commanding a surface ship that could just occasionally dip underwater to hide.
That is a really critical distinction. A conventional submarine is, at its core, battery-operated when it's submerged.
Kind of like a massive underwater smartphone.
Basically, yeah. And just like your phone, if you're running heavy apps, or in this case, giant electric motors to push thousands of tons of steel through the water, those batteries drain incredibly fast.
So to recharge them, the submarine has to turn on its diesel engines.
Right. And diesel engines are essentially air-breathing machines. They need a constant intake of oxygen to combust the fuel.
Which forces the sub into its absolute most vulnerable state, right?
Yeah, exactly. It has to come up to the surface, or at least to periscope depth, to raise a snorkel mast.
Just to literally suck in air from the atmosphere.
Right, sucking in air and exhausting these loud, highly visible diesel fumes. The moment a submarine connects itself to the surface like that, it's just no longer stealthy.
It can be painted by radar, spotted by patrol aircraft, surface ships, all of it.
Exactly. Its entire tactical advantage is severely limited by this constant mechanical need for oxygen.
Okay, let's unpack this with an analogy. It's like a scuba diver.
Okay, I like that.
You can go down, explore the reef, maybe hide in a cave for a little bit, but you're always on the clock.
Right, you're essentially holding your breath.
Exactly. You inevitably have to come back up to the surface. But by contrast, a nuclear submarine is like a fish. It's totally mechanically adapted to just stay down forever.
Because the nuclear reactor completely severs that tether to the surface. It's a total game changer.
So how does that actually work inside the boat?
Well, most modern nuclear submarines use a pressurized water reactor, or a PWR.
Okay.
Instead of burning fuel with oxygen to create heat, they rely on nuclear fission. Basically, they split uranium atoms.
Which generates an insane amount of heat.
An immense amount of heat, yeah. And that heat is used to boil water into highly pressurized steam, which then drives massive turbines.
And those turbines turn the propeller shaft and generate a staggering amount of electricity, right?
Exactly. And once you have an infinite supply of electricity, you essentially solve all the other biological survival problems for the humans on board.
Because the reactor powers life support, too.
Right. It drives a process called electrolysis. By running an electric current through seawater, the submarine literally rips the hydrogen and oxygen atoms apart.
Wait, so they vent the hydrogen and just pump the pure oxygen into the sub?
Yep, right into the submarine for the crew to breathe.
So they're literally manufacturing their own atmosphere from the ocean.
They are. And through powered desalination plants, they are distilling the salt out of the seawater to create limitless fresh drinking water.
Wow. So the vessel becomes a totally self-sustaining ecosystem.
Exactly. With the reactor running the oxygen scrubbers and the water plants, theoretically the machine could stay underwater indefinitely.
But the meatware inside the sub, the sailors, they can't.
Right. Human biology definitely has its limits.
Yeah, you can't synthesize a cheeseburger from seawater.
Sadly, no.
Eventually, food supplies run out.
Yeah.
And I imagine human psychology starts to crack when you trap over 100 people in a sealed steel tube with no sunlight for months.
Oh, without a doubt. The machine will always outlast the human mind and body.
Right.
But what's fascinating is looking at how long the machine itself can run, because not all navies actually fuel these reactors the exact same way.
Oh, really? I just assumed it was a standard process.
No, there's actually a massive operational debate over what actually goes into the core.
Okay, so this is where the geopolitics of uranium enrichment comes into play, right?
Yeah. Yes, exactly. So the United States Navy fuels its submarines with highly enriched uranium, or HEU.
And that fuel is incredibly energy dense.
So concentrated. It means an American submarine can operate for up to 30 years without ever needing to have its reactor refueled.
30 years. That's the entire expected service life of the hull.
Right. You fuel the reactor once during construction, weld it shut, and it never needs to go to the gas station again.
But the downside of highly enriched uranium is that it's essentially weapons-grade material, isn't it?
Yes, and that is the core of the proliferation concern.
Because if an American sub were to sink in shallow waters, or if the tech was somehow intercepted, that material could be repurposed for a nuclear weapon.
Exactly. And because of this, France takes a completely different approach with their Rubis-class submarines.
What do they do differently?
They use low-enriched uranium, LEU. We're talking about fuel enriched to just 7%.
Which is much closer to what you'd find in a civilian nuclear power plant on land.
Yeah, exactly. It's far safer from a global security standpoint.
But the operational penalty for that safety seems pretty brutal.
It really is. Because the fuel is less potent, it burns up faster. So the French submarines must be brought into port, physically cut open, and refueled every 18 to 24 months.
Wow. Think about what that means strategically. Every year and a half, your billion-dollar stealth asset is just offline.
Right, sitting completely exposed in a dry dock for a massive industrial overhaul.
It drastically reduces the overall availability of their fleet.
It does. It's a constant tug-of-war between military efficiency and global non-proliferation standards.
You know, it is wild to think about nations debating atomic fuel efficiency for underwater fleets, especially when you realize how recently this was all just a crazy theory.
Oh yeah, the concept was actually first proposed in 1939 by a U.S. physicist named Ross Gunn.
Wait, 1939? That's long before the atomic bomb was even dropped.
Exactly. But, having the idea and engineering it are two entirely different things.
For sure. It wasn't until the 1950s that the U.S. really forced the nuclear navy into existence.
Right. Largely through the sheer relentless willpower of Captain Hyman G. Rickover.
Rickover had a completely impossible task. He had to take a nuclear power plant, which normally takes up acres of land and requires massive concrete cooling towers, and miniaturize it.
Right. Shrink it down so it could fit inside a 320-foot metal tube.
And not just fit, but operate safely while being subjected to the extreme pressures of the ocean.
And the violent maneuvering of actual combat.
Right. But under his leadership at the Naval Reactors Branch, they actually solved the physics.
They did. In 1954, the USS Nautilus was officially commissioned.
And First Lady Mamie Eisenhower broke the champagne model on the bow of a $55 million machine that completely shattered the existing paradigm of naval warfare.
Absolutely. The moment the Nautilus proved it could stay submerged indefinitely and just outrun conventional surface ships, Soviet Union realized something terrifying.
That their entire surface fleet was suddenly obsolete.
Yes, the tactical advantage was just too massive to ignore.
So it sparked a frantic arms race.
A massive one. By 1958, the Soviets launched their first nuclear submarine, the K-3 Leninsky Komsomol.
And the UK entered the fray too, right, with the HMS Dreadnought?
They did.
Yeah.
But the Dreadnought is actually a brilliant example of how technology was bartered during the Cold War.
How so?
Well, the British submarine was actually fitted with an American S-5W reactor.
Now I have to stop and question the logic there.
Oh, it sounds crazy, I know.
Yeah, I mean, the U.S. had just spent untold millions and over a decade of research to miniaturize a nuclear reactor. It was their absolute greatest strategic advantage.
Right.
You don't just hand over the keys to the atomic kingdom to another country, even an ally, without getting something massive in return.
You really don't. And what the U.S. got in exchange was essentially the ultimate upgrade in stealth.
Really? What kind of stealth?
Well, the U.K. provided highly classified engineering intelligence on submarine design. Specifically, a British acoustic widening technique called the rafting system.
Rafting. Okay, so instead of bolting the noisy reactor pumps and turbines directly to the metal hull of the submarine.
Right, because if you bolt it to the hull acts like a giant acoustic amplifier.
Broadcasting the noise out into the whole ocean.
Exactly. So instead of doing that, they suspended all the heavy machinery on isolated mounts.
Oh, so it's like putting the entire engine room on acoustic shock absorbers?
Yes, exactly. And that's critical because water is roughly 800 times denser than air.
Which means sound travels much faster and much further underwater.
Exactly. In submarine warfare, noise is absolute death.
Right. If the enemy hears you before you hear them, they will sink you.
Precisely. So the U.S. essentially traded raw, brute force nuclear power for British invisibility.
Because a reactor is useless if the sub is so loud it gets blown up on day one.
Right. And that exchange gave the Royal Navy an edge in silent running that the U.S. Navy wouldn't natively match until years later.
That is fascinating. And as the technology matured, the mission kind of evolved too, didn't it?
It did. It wasn't just about attack submarines hunting other ships anymore.
Because the ability to vanish into the deep ocean indefinitely made the nuclear sub the ultimate platform for nuclear weapons.
Right. The SSBN, the nuclear-powered ballistic missile submarine.
Right. The U.S. rolled out the USS George Washington carrying 16 nuclear missiles.
And the Soviets responded with absolute leviathans, the Typhoon-class submarines.
Those things are massive.
They are the largest displacement submarines ever constructed. And the scale of Soviet industrial production during this era was just staggering.
Like, how many were they building?
They were commissioning 5 to 10 nuclear submarines a year.
A year.
Yes. From the late 1950s to 1997, the Soviet Union and Russia built a total of 245 nuclear submarines.
245 atomic submarines prowling the depths. That sounds completely invincible.
It does.
But, you know, the ultimate irony of the nuclear submarine is that the immense localized power that makes it so capable is also its biggest tactical vulnerability.
Yes, it is the inherent paradox of nuclear stealth.
Like, imagine you're trying to hide from someone in a pitch-black room, but you're holding a massively powerful, red-hot space heater.
Oh, I like that analogy.
You might be physically invisible in the dark, but the hum of the heater and the intense heat radiating off you just screams, "I am right here," to anyone with the right sensors.
Exactly. A nuclear reactor, just by its fundamental physics, cannot be simply switched off like a car engine.
Because the nuclear reaction generates lingering decay heat even when it's powered down.
Right, which means the massive reactor cooling pumps must be constantly circulating water.
And water pumps make mechanical noise.
Yes. So ironically, a conventional diesel-electric submarine can actually be stealthier in short bursts.
Because when it turns off its diesel engines and glides on battery power alone, it's almost completely silent.
Right, but a nuclear submarine is literally always humming.
Always. And then there's the heat signature, right?
Yes. A reactor generates an enormous amount of thermal energy. And to keep from melting down, it uses the ocean as a heat sink.
Which means dumping heat into the water.
A lot of it. About 70% of the reactor's output heat is transferred directly into the surrounding seawater.
Wait, 70%. So they are just venting massive amounts of thermal energy into the cold ocean.
They are. And this creates what navies call a thermal wake, or a thermal scar.
Because when you heat water, it becomes less dense, right?
Exactly. So this massive plume of artificially warm water slowly rises from the submarine's depth all the way to the surface of the ocean.
Wow. So even if the sub is cruising silently hundreds of feet below, its exhaust heat floats to the surface like a thermal footprint.
Right. It might be totally invisible to the human eye, but if an enemy patrol aircraft flies over with forward-looking infrared or FLIR sensors...
That warm water on the surface lights up like a beacon.
Exactly. The very thing that grants them limitless endurance is the thing that can expose them.
That is such a huge paradox.
It really is. But, you know, the dangers are not just external enemy sensors.
Oh, right. Trapping people inside these things?
Yeah. When you trap dozens of human beings in a sealed tube filled with high-voltage electricity, pressurized steam, high-explosive torpedoes, and a literal nuclear reactor.
The margin for error basically drops to absolute zero.
Right. When things go wrong in the deep ocean, the human cost is catastrophic. The history here is incredibly grim.
Yeah, let's talk about some of those incidents, like the USS Thresher in 1963.
Right. The Thresher was conducting deep diving tests off the coast of Massachusetts.
And from the sources, it looks like a piping failure likely caused a flood.
Exactly. A flood which shorted out the electrical systems, and that led to a reactor shutdown.
And without propulsion to drive the sub toward the surface, it just sank below its crush depth.
Right. All 129 crew members and shipyard personnel died instantly.
Just horrifying, though it did force the U.S. Navy to implement the SubSafe program, right?
It did, completely overhauling how submarines are designed and inspected from top to bottom.
But the Soviet naval record is marked by even darker incidents.
Yeah. For example, the K-19 in 1961. It actually earned the dark nickname, the Widowmaker.
That's ominous. What happened?
It suffered a complete loss of coolant accident in its reactor.
So to prevent a total nuclear meltdown, the crew had to literally jury-rig a secondary cooling system using welding equipment.
Right, exposing themselves to lethal doses of radiation in the process.
8 men died within days from acute radiation sickness.
And dozens more suffered severe long-term health consequences.
Unbelievable sacrifice. And then there's the tragedy of the Kursk in the year 2000.
Right, which really highlighted the dangers of the weapons these machines carry.
Because the Kursk suffered a leak of highly volatile hydrogen peroxide, right?
Yes. Hydrogen peroxide is used as a propellant in certain torpedoes. It's a highly reactive oxidizer.
And a faulty weld allowed it to leak and react with a catalyst, causing a massive internal explosion.
And that fire then triggered the detonation of half a dozen other torpedo warheads in the forward compartment just minutes later.
The blast completely ripped the front of the submarine apart.
Right, sinking it to the bottom of the Barents Sea. All 118 crewmen were lost.
It is just a sobering reminder that the ocean does not forgive structural failures.
No, it really doesn't.
But for all their heavy armor and atomic power, these billion-dollar leviathans can be shockingly fragile in the most mundane ways, too. Look at the USS Miami in 2012.
Oh, the Miami is a perfect example of unexpected vulnerability.
It was an elite Los Angeles-class attack submarine.
And it wasn't destroyed by a Soviet torpedo or a meltdown or a pressure failure.
It was destroyed by a disgruntled civilian shipyard worker who intentionally set a fire with a lighter in the forward compartment while the sub was docked for maintenance.
Right. One guy, a lighter, and some rags caused an estimated $700 million in fire damage.
And the Navy evaluated the hull and realized it was simply too expensive to repair. They had to scrap the entire submarine.
Over a small fire.
Which brings up a massive logistical question.
How do you throw away a nuclear reactor?
Exactly. Because if the salt water is eating the hull for 30 years and the metal is suffering fatigue from constant pressurization cycles, eventually these machines die.
Right. And decommissioning a nuclear submarine is a total financial nightmare.
Like, how much are we talking?
Well, in 2004, the estimated cost of properly disposing of these aging fleets was around $4 billion.
$4 billion. That's insane.
Yeah. And historically, some navies thought about taking the easy way out. Just defuel the reactor, seal up the heavy steel hull, tow it out to a deep-sea trench.
And just let it sink to the bottom, out of sight, out of mind.
Exactly. But obviously, you can't just drop radioactive material into the ocean anymore.
No, international laws, specifically the London Dumping Convention and the Law of the Sea Convention, strictly prohibit the dumping of radioactive waste into the marine environment.
So sea disposal was universally taken off the table. Navies have to dismantle them on land.
And reading about the dismantling process, the fuel itself undergoes a terrifying transformation during its 30 years inside the reactor, doesn't it?
Oh, it absolutely does. The uranium-238 doesn't just burn away like coal in a furnace.
Right. The sources mention it captures stray neutrons during the fission process and transmutates.
Yes. It physically changes on the periodic table into completely different elements, like plutonium and minor actinides.
Wait, so what happens to that toxic cocktail when the sub is chopped up?
Well, that transmutation is the heart of the disposal crisis. You aren't just dealing with spent uranium, you are dealing with plutonium.
Which is incredibly toxic and highly radioactive.
Right, and it remains a hazard for tens of thousands of years. It's a toxic cocktail that requires meticulous handling.
So what do they actually do with the physical submarine?
They drag the submarine into a dry dock, extract that highly radioactive transmutated fuel, and then shipyard workers literally cut the submarine into pieces.
They slice out the entire reactor compartment, right?
Yes, the heavily shielded steel cylinder that housed the nuclear core. They weld heavy steel plates over the open ends.
And then transport it by barge or rail to a designated secure low-level radioactive waste site where it's buried in the desert.
Exactly. It is a massive, sprawling industrial cemetery just for radioactive submarine parts. And if we connect this to the bigger picture, when you compound this disposal nightmare with the extreme risks to human life and the inherent tactical vulnerability of a noisy, hot reactor in the ocean.
Navies are looking for a radical shift in strategy, aren't they?
They are. The ultimate solution to the human cost and the thermal wake is to completely remove human sailors from the equation entirely.
So we're talking about the dawn of nuclear-powered drones.
Exactly. For example, by 2027, the Russian Navy plans to deploy a system called the Poseidon.
The Poseidon. That completely rewrites the rules. It's an unmanned, nuclear-powered, and nuclear-armed underwater vehicle.
Right. And because it doesn't need to support human life, no oxygen scrubbers, no desalination plants, no bunks, no food, it is much smaller than a traditional submarine.
And it utilizes a miniaturized reactor that lets it travel at a staggering speed.
Roughly 130 kilometers per hour underwater.
That is incredibly fast for underwater travel.
It is. And its strategic purpose changes the calculus of nuclear deterrence entirely. It's designed to be carried by and launched from a specially modified mothership, like the Russian submarine Belgorod.
So instead of a traditional ballistic missile submarine having to surface or launch a missile,
Which creates a massive acoustic and thermal signature.
right, instantly revealing its location and virtually guaranteeing it'll be hunted down and destroyed, instead of that, the mothership can just quietly release this drone in the deep ocean.
Exactly. The mothership stays hidden and safe. It deploys the drone, which then travels autonomously toward its target.
So the Poseidon acts as an ultimate second strike weapon aimed directly at coastal cities or naval bases.
Right. The location of the human crew on the Belgorod is never revealed, and crucially, no submarine crew lives are automatically sacrificed in the strike.
It effectively removes the human element from the frontline delivery of mutually assured destruction.
It really does.
As we transition from these massive, crewed submarines to automated, nuclear-armed underwater drones, the entire architecture of naval warfare is clearly shifting.
It is. It really brings us back to the duality of the nuclear submarine.
Right. On one hand, it's undeniably one of the greatest marvels of human engineering.
The ability to pull oxygen from seawater, to harness the power of the atom in a pressurized steel tube hundreds of feet underwater, to stay hidden for months, it is an extraordinary technological leap.
But that same marvel carries a devastating financial cost, massive environmental hazards that will require active management for millennia.
And a tragic human toll that is absolute when structural limits are exceeded. From the Thresher to the Kursk, the ocean just does not offer second chances.
It really doesn't.
And this leaves us with a chilling final thought to consider.
Okay, what's that?
Well, we're watching nations like Australia, Brazil, and North Korea actively race to build or acquire their own nuclear submarine fleets.
Right.
At the exact same time, the superpowers are transitioning toward unmanned, nuclear-armed AI drones like the Poseidon.
Right, removing the humans completely.
Exactly. So are we slowly turning the global oceans into a fully automated atomic minefield?
Wow.
When these autonomous nuclear-powered machines inevitably outlive the navies and the political systems that built them, who exactly rules the deep?
Imagine a future where the oceans are populated by silent atomic machines that don't need air, don't need food, and don't need orders. It makes you completely rethink what it means to conquer the deep ocean.
It certainly does.
It's not just about humans surviving the crushing pressure anymore. It's about the rest of us surviving the very machines we've put down there.
Thanks for joining us on this deep dive. Keep questioning what's beneath the surface.